Duga, the most ambitious Soviet project of the Cold War. A system designed to detect the launches of American ICBMs. Yet, due to the Chernobyl disaster, it never reached full operation. Still, in the shadowed halls of its data center stands the K340A, a one-of-a-kind computer that once served as the brain of this monumental system. This is the first ever documentary dedicated to this machine, its history, hardware, design and operation. And it is the first of few stories from our nearly 10-year research into Duga that we believe will finally answer some long-standing questions about this place. For the first time, we went to Duga in August 2010. Well, I have just a few blurry pictures from that visit, and back then Duga was almost completely off limits. Trees were growing through antennas, there was moss under them, and all that looked like a relic of a lost civilization surrounded by ruins of an ancient city. But main mystery obviously was not here, but in former machine halls, filled with cold, moisture and heaps of deteriorated equipment. But what looked as a chaos obviously had a logic behind, and I could not get from a feeling that some answers are right in front of us. As it appeared later, I was completely right. During next few visits, I explored the biggest structure, the data center, to make sketches of the floor plans. And at the upper floor, in one of the large halls, were standing rows of racks marked K340A, along with the operator consoles. And just a quick look at the inscriptions cleared it out. That was it, the mysterious control computer I only heard about. And it looked not even close to anything I saw before. It was here, and at the floor below these halls came a lot of cabled racks. At that time, apart from a few news articles and some forum posts, there were almost no details about Duga available, not even speaking about its computer. It was like this up to late 2014, when I accidentally got a book by Boris Malashevich, who is a very serious researcher of Soviet computer history. And there were these pictures, which were the first and still the only public images of an intact K340A computer. He took them at Duga-3Y radar system in Russia. That is the only place except Duga where these computers were ever used, and the last where a few were still operating. He shared quite much technical details, including that the computer was based on the Residue Classes Systems of calculations. He also claimed that it was the fastest second-generation computer ever built. And back then I realized there were just 50 of them ever produced, so that can become an absolutely fantastic museum exhibit, and we need to do our best to save it for posterity. But first we needed more information. In late 2016 we returned to Duga for a research expedition. We wanted to map the remaining computer equipment, but more importantly to look at the remaining documentation. Well, if you have been here on tours, you surely saw those papers scattered everywhere, but I guess not so many actually tried to read them. So we brought a tripod with a camera, also other equipment, and started to work. Mostly that was trash, but a few papers had parts of blueprints of the computer racks and other visual hints. Practically everything was very heavily affected by 30 years of exposure to moisture. So it took us a lot of effort, but some we could turn from this into this. Well, now I see it was a good idea because Duga already had become a tourist site. Because quite often people having no bad intentions were moving papers to take a better picture, then next day rain came, and then many things were gone. Also, there were a few pages from a technical description, which explained how worked printers next to operator's console. Fast forward, with this information later we could find exactly the same printer and even develop a controller with the USB interface for it. Well, about this we'll have a separate episode. But you may wonder, why all that was left behind? Well, in fact, remained very little. Attempts to revive the system continued up to 1988, but with no success. And after everything sensitive was completely removed, Duga's site became a civilian object, and what was left behind was basically nothing but trash. But it helped us reconstruct how the K340A looked when it was intact. Still, that didn't explain why so strange computer was actually needed at the first place. Well, as you will see next, later many answers came from the history of its creation, but before happened one very special meeting. One day, an elderly engineer, whom we'll call George, requested a tour to revisit his former workplace. He wanted to show it to his grandkids, because they read something on the internet, became interested and started to ask questions. This wasn't unusual, because many engineers had done it before and many did after. But when we met, he said he worked with ES-1033 general-purpose computer which was in the hall at the third floor. While it wasn't directly involved in Duga's operation, it was used for mathematical research. Of course, I asked about computers, and he told this. Those special computers were serious and strange. Only a small number of engineers worked with them directly, and they were mostly in their late 40s, so now they are over 80. Well, I know a few, but I'm not sure how I'd connect you with them, because there are age-related issues. However, from what I recall, there were initially 7 computers, with one more added in 1985. They did many things, but 2 tasks stood out: processing trajectories and optimizing frequency-angular modes of operation. We later visited what left of his machine, where he shared some really epic stories, including how a little prank with K340A hardware caused a big mess. But then he explained. In simple terms, Duga's transmitter sends signals towards the start point of an ICBM. The signals bounce off the ionosphere multiple times to reach the target, which is the missile's engine's emissions. Then the signal reflects and being received by 2 receivers which triangulate and track its position. Well, it sounds simple, but in reality it is much more complex, because features of ionosphere's layers vary with time, seasons, geomagnetic activity and dozens of other factors. So an algorithm running on several K340A machines analyzed these conditions and suggested optimal operating frequencies. And once a target was detected, other K340A machines processed this data to determine the trajectory and predicting where and when it would reach its destination. This required fast processing of enormous amounts of very long numbers. Well, today that is not so difficult, but in the 50s and the 60s, computers were based on vacuum tubes and individual transistors. So performance, reliability and energy consumption were significant challenges. This is why a very special computer was needed. In the 1950s, Czechoslovak professor Antonín Svoboda and his student Miro Valach developed an elegant solution. So imagine you have a very huge number to process. You also have several buckets with different number of slots. So you make the integer division by each of these, placing the remainder into a bucket. This method is called the Residue Classes System, or RCS. So you can represent large numbers as these small residuals, and when you make operations like multiplications or addition, you now work with those small numbers. In the late 50s, a report on Svoboda's research caught the attention of Theodor Lukin, head engineer of Design Bureau 1, which was specialized in Soviet air defense systems. He forwarded it to Israel Akushsky, who later became one of key developers of K340A. He realized that the new system has limitations, so it cannot be universal, but still it can be a great deal for specialized machines. So he shared his ideas with his boss, Davlet Girey-Yuditsky, who was previously a developer of Strela and Ural computers. In 1960, Lukin became the head of Institute 37, later known as the Institute of Distant Radio Communication, and he invited both scientists for a new job. A decade later, in this institute, Duga was designed. First, they created A340A, an experimental 20-bit machine capable of 5000 operations per second. Then was T340A, a second-generation RCS-based computer built on ferrite transistor logic. And finally, in 1966 was finished K340A. A 1972 report by Yuditsky and Akushsky reveals some interesting details. So they patented their innovation in several countries, including the United States, France and the UK. The K340A had 472,000 elements, including 80,000 transistors, with an algorithmic performance of 1 million operations per second. Each machine cost 1.2 million Soviet rubles, which are roughly equivalent to $2 million at the time. By then, 10 machines had been produced, 2 were in adjustment stage and 15 more were planned. The first K340A was successfully tested at the 5N11 site. That was the initial Duga radar installation near Mykolaiv, here in Ukraine. So, a standalone K340A consisted of 15 to 17 computer racks, 4 power supply racks, an operator's console and a table-shaped rack with 2 connected printers for output. The operator's console was relatively small, and likely it was used only for maintenance and overall control. It featured light bulb-based indicators with masks with inscriptions and blue and orange filters. Well, we could decode purpose of most of controls, but it is easier to explain this in connections with the racks. So all racks were standard for NIDAR equipment and they housed small standard cards. Like this one, which was saved from the Mykolaiv Duga by someone involved in its dismantling in 90s. Unlike the Chernobyl Duga, where every card lost its silver connector, this one remains completely intact, and it has these 2 metal bezels. These cards, called cells in K340A terminology, were actually very simple devices. We estimate there were around 50 variations of these cells, and many of them we could identify. Depending on the size, a cell could occupy 1, 2 or 3 slots, with up to 50 slots per one row. Each slot was equipped with a custom 35 contact connector made of epoxy resin, to which wires were attached using wire wrap. Each row also had 2 power buses and large connectors for cables that linked the racks. There were 3 types of racks used, and the first was the data processing rack. There were 4 of them in each machine, forming what we would call now a processor. So inside were 12 rows containing of total 600 cells. Rack A3 controlled all the computer system. A4 served as a high-speed processor buffer for 16 45-bit words. And racks A5 and A6 were the arithmetical logical units that handle Residue Classes System calculations. The second type of rack was so-called one-side accumulator. There were either 3 or 5 of them. Rack A7 stored constants and others stored programs. Each had a capacity of 4096 45-bit words. And since these constants and programs were very rarely changed, there were no need for, say, tape reels or punch cards. Instead, each rack had 4 large crates, each holding 32 so-called cassettes. Each cassette featured a 2-layer matrix with openings and coordinate rulers. In every opening there are 2 coils, where are tiny ferrite rods to be inserted in one of 2 positions. 1 inductively connected coils to indicate a logic of 1, while partially inserted rods represented a logic of 0. This feature is tied to the story of a prank George told us about. When one of the machines was being commissioned, the cassettes kept giving wrong data no matter what. So engineers reinstalled the ferrite rods repeatedly, but each time the errors would pop up in different places. This went on for weeks, throwing us way off the schedule. Eventually some very serious people with cold eyes showed up at the data center, well, if you understand whom I mean. They started to ask questions and putting everyone under immense pressure. During yet another attempt to fix what looked as a faulty cassette, one engineer had his hands already shaking. So he accidentally dropped a box of ferrite rods on the floor, and of course he tried to pick them up with a magnet. But to his shock, some of the rods weren't magnetic. It turned out that some prankster had made a few dozen similar looking rods out of pencil cores and just mixed them into the box. Well, maybe it was done even at the factory, but the story eventually spread all over the data center, and a year later we of course laughed about it, but at that time, trust me, it was anything but funny. Data reading was partially handled by 9 XY decoders on each cassette. And between the crates of cassettes there are 2 lines of cells. Some of them were address formers, controlling a diode-based decoder with 4096 outputs. The selected data passed through amplifier cells and then was sent to the processor buffer. The RAM of K340A consisted of these 8 racks, numbered from 8 to 15, and they were called accumulators of numbers. Each rack housed two independent accumulators with a capacity of 1024 45-bit words. Well, unfortunately we do not have detailed information about them. But a photo by Boris Malashevich shows that inside were two mirrored sets of cells and four extra power supplies providing 27 volts. A key feature of the K340A is its advanced system for interacting with external devices, so up to 8 devices can be directly connected to the processor controller. But additionally, any of the accumulators of numbers can be deallocated from RAM space. In this case, they would act as some sort of buffers for data exchange with these external devices. All computer racks were powered by a 4-rack section named K340A. Well, its racks are now empty, but backplanes and tables are still inside. So that helped us to precisely identify the layout of one of them. The first rack had warning lights indicating how power was controlled, either remotely when a part of multi-machine complex or locally from the console. The console also has similar indicators, a mode toggle switch and a compartment with switches to adjust power voltages in local mode. However, as you can imagine, all this equipment generated significant heat. So a powerful air conditioning system was installed in the second floor, with each segment cooling 3 to 4 racks. Air was circulated through the racks, collected at the top and then recirculated for cooling using two collectors at the edges of each row. George shared two stories about this cooling system. Our machinery needed a special climate to operate, so it was always quite cold inside, around 20 degrees Celsius. In summer we often went outside during breaks, so trust me, we learned how to get a cold from air conditioning long before it became common knowledge. But there was a more serious incident, so there is that huge hole, right? Here stood two very large air conditioning units. The air was cooled with water and there were special dryers. One day one of them malfunctioned and the issue wasn't detected in time. To our horror, we found literal drops of water inside the equipment racks. You can't even imagine how much equipment we had to repair after, or how many people lost their job over it. Also on the second floor was a large system of cable mounts along with those small racks marked K341A. They had an interesting function, so connection between racks were made using coaxial cable. However, thin cables with small connectors that fit neatly were limited to a length of 12 meters, but some connections needed to span over 100 meters, requiring thicker cables. So these small racks contained cells with passive splitters, basically blocks of resistors that allowed cables of various types and resistances to work together. There are no exact details on how to operate the console, but at the same time this is a machine from the epoch where you would work with data on a very low level. So it is possible to approximately understand what was what. The central section features long rows of 45 light bulbs. Its upper part displays the registers which contain the data being currently processed. And based on this inscription, these light bulbs are grouped by the moduli of the Residual Classes System. Then there are these two registers with unknown purposes, and below are registers of two arithmetical logical units. These likely display the final computation results from each unit before the data is sent further to the processor buffer. And then it's interesting, so at the bottom there are control register of instructions, which showing the current instruction, and the register of instructions, which likely displays the operator's input or queued instruction. But here is interesting detail, so the computer could perform two instructions in one. The 25-bit long is called K2 and it is for managing data exchange between the processor buffer, storage devices and external connections. And another part, which is 20 bits long, is called K1. It is for arithmetical logical units, so this is why this indicator is split to two parts. Indicators on the right likely display addresses of data and instructions being processed, as well as the processor operations and system status. Then on the top left there are three rows of light bulbs which indicate status of system interrupts, which are blocked, which are enabled and which are triggered or currently active. The K340A had a special time register and time counter, but also it had a real-time clock in the most literal meaning. That was technically a standard aviation clock that generated impulses. Below this are small indicators for devices exchanging data with the processor. And also 2 rows of light bulbs indicated which RAM units are used for actual RAM or which are deallocated for external data exchange. Then there is a keyboard. Well, some buttons are missing, so we needed to make a combination of pictures of a few panels. Well, no inscriptions remained on any, but the functions became clearer when we examined the internals of the panel. So shortly, everything on the right are various blocking and console commands corresponding to the indicators above. Then 2 bottom rows are for the operator's input, to enter K1 subinstruction, K2 subinstruction, and this longest row is to enter values. Next are start, stop and step buttons. Everything else are buttons which allow to modify, select and override data, addresses and instructions. Except this one, which activated the built-in loudspeaker for announcements. The output of operations was on a paper tape, coming from MP16-2 numeric printers. Those were common in the 60s for various computers and industrial devices, so well, it took years, but we could find one. The machine had one active printer and another was in backup. Although we do not have any details on actual output intensity, we know that the printer could produce 25 rows per second, and one paper tape could hold 20,000 rows. But here is a tiny detail: the printer could print 16 symbols in a row in decimal or octal format. But K340A operated 45-bit words, so what looked as a table for printers is actually a controller rack that converted that into a format compatible with the printer. We will soon do a detailed review of this printer and demonstrate how it works, so stay tuned. On internet you can find that these computers were part of a larger processing system called 1S31G. There are some limited details about it, but there is also an evidence that there was actually unfolding quite a dramatic story behind. So on each console there are small orange signs with numbers of machine sets, or so-called MKs. Initially there were 7 of them, 6 in this hole and 1 in the next. Some MKs had extra racks which doubled their storage capacity. And given that power system could operate in centralized control, some machines had to be in hot reserve for extra stability and redundancy. That shared power controller had to be somewhere close, so we believe it was in this now empty room. There is another tiny room that our engineer mentioned. In this room were standing a few hard disk drives, the same as YES mainframes had, and their controller rack. So all the data from K340A was streamed to those disks. Well, where those went, I have no idea, unfortunately. Our guess is that the data went to NIDAR Institute for research purposes. Because despite Duga never being on active duty, it was somewhat operational and much ionospheric research was conducted. This connection was likely managed by these racks, because one of which is extra pairs of number accumulators, which, as we told before, could be used as a buffer. There is a well-known story that in 1984, after many tests, designers concluded that Duga as it was ineffective. That led to a decision to use more complex algorithms for its operation. That needed more computing power, so later an 8th set, MK/08, was added, and integration work started. But in rows of K340A there are more racks, which have code S27 in them. Logically, those must be some sort of communication interfaces, because a standalone machine is completely useless. However, visually the design of few of those looks not only different, but somewhat handmade. And here we can only guess, that was one-time creation, likely for some very narrow use, for this very place. And we believe that could be only one thing, a connection with new mainframes. Those were installed in 1984 at the first floor hall. Those were YES-1060 Soviet IBM 370 clones with a performance of 1 million operations each. That was obviously unplanned, because to fit their cable connections the floor was raised. George said that these machines were at the adjustment stage and never went into operation due to the Chernobyl disaster. As a side note, our longtime followers remember we found the control panel of a similar mainframe and are working to bring it back to life. This project is going slowly due to limited information, but we hope to finish it this year. It looks like that these mainframes were installed as a last resort, because civilian computers had a weak point in simultaneous processing of external connections. That's why in 1986 Duga was still running on computers designed in 1966. But it seems that that was no longer sufficient. And that brings us to somewhat unexpected conclusion. Maybe the Chernobyl disaster, which effectively ended this project, was actually a huge relief to everyone. That allowed to leave all behind and finally forget it. Back in the day, what stands in this hole only cost roughly 15 millions of US dollars. But for the Soviet system, which operated astronomical budgets, this was not more than a matchbox price. But overall expenses were obviously hundreds, if not thousands times higher, and that makes Duga a monument to real priorities of the Soviet Union. The country which invested in this, but not in the safety of nuclear power plant located nearby, and that eventually brought its fruits. With all that said, our research always had a bigger goal, to preserve at least something from K340A and to tell this dramatic story. This led us to the idea of creating a Cold War museum in one of the buildings at Duga installation in Chornobyl too, with a part of K340A as the central exhibit. While there isn't enough information to make the machine functional again, the plan was to clean and repair the components. Then assemble them like a model wired to a modern computer to recreate the lights and sounds. So anyone would be able to sit at the console and feel as an operator, or study papers, or look at electronic parts, and so on. And by 2021, we had an official work group with many people involved, and we were very close to starting actual works. Unfortunately, then happened February 2022, and this postponed everything indefinitely. One day, if the data center building remains stable enough, we will return to this project, but the story likely will be different. Until that time, we will do our best to save the story of Duga in digital form, and this is the first of them. So stay tuned, thank you for watching, and see you next time.